Hello, Colin and Sawyer. Feel free to ask me questions if you have any. I just came in early in case anybody had questions. Thank you. Let's see if I can remember to tell everybody to do that when class starts.
Since the test is due on, or the chapter one and two test is due on Sunday,
Hmm.
we don't need to schedule time to meet with anyone to proctor it. It's like time by itself, right?
Yeah, this is an online test. You get multiple attempts. I think I normally give you at least three. And it's open book, open notes, open other books, open other notes, open Google searches, all that stuff you can do. The only thing is you're limited a little bit on time. And when you take multiple attempts, it's a different set of questions each time you take it. And the only thing you're really not supposed to do is not look at anything that someone might have created after they looked at my specific test. So, if a student got online and took the test and then made a web page out of uh, what he learned from it and how to solve those problems, that would be something you wouldn't be allowed to look at. So I try to do the wording and the explanation so that that is excluded. But other than that, you can pretty much do anything. It's really about your chance to get a little improvement on your score while learning how to expect what tests are like by me.
Okay. How much calculus will really be involved in the test overall? Just because, like, we started going over calculus a little last time,
Hmm.
and calculus isn't my best subject.
Right. You'll
Overall, like
see the
I
worst
know how to
case
do like the
scenario of
basic
that.
following like the formulas and stuff and using that, but you actually using calculus to like get it out, that's a bit more
So
difficult.
I showed you last time the derivation of the kinematic equations by solving a differential equation. And that gave me, V equals V0 plus AT.
Yeah.
And then again made another differential equation and solved that, getting X equals 1 half AT squared plus V0 T plus X0. That process I'm going to show you again today in an example. And that's sort of the worst case scenario of what you could expect on this test. But that is
All right.
very much calculus. You are integrating and stuff like that.
Okay, because yesterday I had time to go over the chapter two conceptual homework,
Right.
and the last question was like something along the lines of like T equals D to the third or something. And
Hmm.
even though I watched like the video they had you ahead of time, I was very confused on how they got there on that one because it didn't seem to match up.
Gotcha. I'd have to look at that question specifically to address it, and I don't remember it off the top of my head. I'm not sure if that's a calculus one. It sounded to me like it could have been one that was related to units, but I'm not really sure of that either.
It was definitely calculus. It was like similar to how the derivations were got, but it was just
Oh, okay.
it didn't seem to click in my brain.
Well, when you watch the derivation, it's the third problem I solved today. So when you watch that, hopefully that'll give you a little bit of an idea. But by all means, if you want to, I mean, I know it's a little late, but if you want to, send me a picture of the problem that you're talking about with if it's multiple choice, make sure you include the answers. But send me a picture through my cell phone and I'll give you some pointers on it or even solve it. And sometimes when students ask questions like that, I sometimes just make a whole video showing them how to solve it.
All right.
So anything like that's fine. But yeah, we do have a test coming that's due Sunday at 11:59 p.m. So make sure you guys get that. The good news is, like I said, the practice test has been open since the first day of class. The online test has been open since the first day of class. And if you take the practice test enough times, then in principle, you will have seen every question that could have popped up on the actual online test because I haven't added any additional questions beyond what's in those test banks.
Okay, that was my last question was like for studying for it is like I remember you saying something originally about like the test would only have like a fifth of what the practice test only had like a fifth of the questions on there.
It's
But
the
was that just like did you actually mean just like volume or like what it covers? Because I assumed you meant it only a fifth of what was covered by the test.
No, it's actually even better than that. So basically, I guarantee you that 20% of, or excuse me, the 80% of the points that are available on an actual test will have been problems that you had the opportunity to see through the practice tests.
Okay. And
Uh,
just 20% aren't covered.
yeah, the 20% are not covered, possibly. But to be honest with you, in the last 10 years, I haven't added any of those questions. So it's literally 100%.
Okay. All right.
Okay.
Thank you.
If I saw students that seemed like they were sort of, gaming the system or something like that, then might be compelled to add a little bit more from time to time. The only thing I've done to date is occasionally I'll turn one from a multiple choice problem into a free response problem, but it's still the same problem. It just might have slightly different numbers, but it's identical.
Honestly, I used to find like written out free response better than multiple choice because multiple choice, it's like, hey, it could be any of these, and then my I get confused and second guess myself. But at least with the free one, you can see what I was going for and
Exactly.
how I might have gotten that.
And what's worse is these multiple choice questions that I choose are actually really good in that, like, answer A, it would be a common mistake students make, and the answer you'd get if you made that mistake, answer B would be a similar but different common mistake students would make, and then C would be the actual right answer, and then D would be something that would come up from just forgetting to convert units. So it's actually a really rigorous online multiple choice test. It's not a trivial multiple choice test.
Yeah,
If my classes were smaller, I'd prefer to just grade a free response test. But man, I get so many big classes, it's really hard to grade that many.
I noticed that on, I forget which question it was, but one of the chapter one homework ones,
Hmm.
I made a like a mistake during it because I didn't, I think it was like I didn't notice that the quote, the brackets had ended. So I
Right.
made like a small mistake
Oh,
there and got exactly one of the wrong answers. It was like exact. It was like, I think I just made that obvious mistake.
yeah, that's tough. I worked for Prentice Hall doing the online homework system and some of the test bank questions for Giancolli's textbook, and that was some of the hardest work I did was actually trying to work out the common mistakes students made and then make an answer for that. And then make it for all the different versions because we'd have it at least on the online homework system. Each time you do it, the numbers are different. So I'd have to make it an algorithmic problem that would make up a new problem, make up a new solution for each different number, and still had those common mistakes in it. But yeah, that's the beauty of this, and that's why one of the reasons why I still like using Giancoli is because I know exactly what went into it. I've done other books too, so I use those as well, but they're almost all Prentice Hall and Norton publications. So hopefully, like I said, they are really good questions, and they're the only multiple choice that I'd really feel all that comfortable using. Those and the other ones that I've used in the past, just because I've worked on them and I know exactly what went into them. Or in other cases, I've actually had enough experience with using them that I know they're good. But yeah, you got to watch out for that. When we do the face-to-face test, I'm probably going to have you guys be able to turn in your work. So I might work to try to give you partial credit, even though the multiple choice answer is just right or wrong. If you get a wrong answer and you turn in your work, I'm going to try, if I can do this, I'm going to try to skim through those and give you, points here and there for making good decisions and good attempts at solving the problems, even if you got the wrong answer. So I can't promise that. That's why I didn't put it in the syllabus, but that's what I'm shooting for. Anybody else have any questions? We got about a minute left.
Yeah, where's half the class?
Yeah, it's not a very big group here. We only got 10 so far. I might have scared them. Oh, got another one coming in. I'm a little scary sometimes because I really cover a good rigorous a course or make a really good rigorous course and cover some, some of the tougher stuff as you'll see today when I do this third example. Uh, But I really, really, really do not recommend my students dropping. I can, I can move heaven and earth to try to help you guys. So just let me know what I can do to help you, and I'll do it. Or tell me what your problem is, and I'll figure out what I can do to help you. And it's very rare that students come to me to get help and still fail. And I'm not saying that because I pass them because they come to help me. I'm saying that because I work hard to make sure they understand it well enough so that they can pass on their own. All right, it's time now. So I'm going to go ahead and make a big announcement. Oh, I say a big announcement. It's something you already know. It's basically letting you know that, hey, you have the end of chapter one homework might still be due, or, chapter two homework might be due this weekend. I think that's what it is. But the thing that really is the bigger idea is the fact that we've got our first online test, and that is due Sunday at 11:59 p.m. So everybody, please make sure you get your online test done by 11:59 p.m. Sunday. The very best thing you can do to prepare for it is take that practice test as many times as you can. I've seen students sometimes take it 25, 30 times. And if you can, consistently, like two or three times in a row, get an 80 or higher without having to look up any questions or look up the way to solve any of the questions, like I said, two or three times in a row, then you're probably in a pretty good spot where you can successfully at least pass the test, if not do pretty well. If you're getting higher than that, then yeah, you probably get 100. But generally speaking, students that get, two or three 80s in a row without looking up stuff are generally in a good spot to make somewhere in the B range at least. So do that as best you can. Make sure you get it done on time, but do the practice test. Not only that, remember the online test. The rules are you're allowed open book, open notes, open Google searches, open other books, open other notes. The only thing you're really not supposed to do is in any way get any help from someone that has seen the test. So you don't want to, what I normally tell my students is specifically don't look at anything that was created after the day I published the test online. This first test was published on the first day of classes, so that's really a big gaping hole. Don't look at anything published on the internet or anything like that since the first day of class. I say that, but what I'm really meaning is I don't care if something's been published since then, long as it isn't coming from someone who has seen my test and therefore created something to help you from that test. Okay. All right, so let's go ahead and get started, everybody. I'm going to go ahead and share my iPad screen with you guys. Looks like I've got the right page dialed up. Feel free to ask me questions as we go. Uh, I don't think there's anything else I want to say, but just make sure you get your homeworks done like you're supposed to on time. And then the other thing is make sure you get the test done this weekend. And if you're having problems, including over the weekend, remember I always told you if you can take a photograph of the actual problem you're solving, if it's a multiple choice, make sure you include the multiple choice answers. But take a picture of that and tell me what problems you're having if you can articulate that. And I understand a lot of times you can't say exactly what the problem is, but if you can, do tell me. And I will gladly, tell you how to fix it. If I get enough questions about the same question, what I normally do is just create a solution, like on a video setting, and then I post it to my YouTube channel, and then let everybody know that it's there. But the big thing that you should do is go to my YouTube channel and go ahead and subscribe to it, and then make sure you've got your notifications on because every time I publish something to my YouTube channel, it would be ideal if you guys would get an email about that. You will be able to tell if it's something for your class, and I just would like you to know once the class is over, unsubscribe. You don't have to, keep getting emails from me. But the main thing is, I just want you to be alert to whenever I post something on there because sometimes I'll have a gap of time in the middle of the week and I can post three or four videos. Other times I go months at a time without posting anything. All right, let's begin. So this is example 216. Again, I'm typing these up in such a way that I'm hoping I'm not violating any copyright rules and stuff like that. So I'm trying to be as faithful to Giancoli so that it's helpful to you as I can, but also not faithful enough to where I get in trouble for posting stuff on the internet. So consider a ball thrown downward with an initial velocity of 3.00 meters per second. A, what would be its position relative to the position at which it was released after 1 second and after 2 seconds? B, what would be its speed at those times and how do they compare to the speeds of a drop ball? Ignore air resistance. So that's what we're trying to do. Oh, yeah, I should go ahead and remind you guys. The other thing I was trying to remember to tell you is go ahead and chat me your first and last name. It looks like most of you have already done that, but if you haven't, go ahead and do that. So we're going to start off with a solution. So I think, anyways. Okay, solution. My pencil wasn't writing for some reason. And what I'm going to tell you is in this case, we're asking for some specific information. What we're told is the initial velocity is 3 meters per second downward. So V0, notice that's part of the physics that you're learning is when you see a number, you should not only be able to assign it a symbol like V, but you also might need to assign it a subscript like 0, meaning its initial. Okay, so I'm putting 3.00 meters per second, and I'm going to say down, and that really means downward. So I'll put a dot after it, so it looks like an abbreviation. Uh, the reason why I say that as opposed to picking a sign is because at this point I haven't decided which direction, or I haven't specifically told you which direction I'm going to call the positive direction and that sort of thing. Another thing, it says consider a ball thrown downward with an initial velocity of 3 meters per second. The fact that it's thrown downward is clearly covered by us having a velocity of 3 meters per second downward, but it also implies that we're somewhere probably where gravity is acting, in which case I'd assume the Earth, because he didn't say it was on another planet. So I'm going to go ahead and say that the acceleration is 9.80 meters per second every second, and I'm going to say down on that one as well. Okay. What would be its position relative to the position it was released? So, since I said relative to the position at which it was released, I'm going to call the position at which it was released x0 because that's what x0 means. And to make it relative to that, it'd be really nice if I called that position x0, so or 0. So I'm going to say x0 is equal to zero point 0.0 meters. Okay, so there's another piece of data that I can write down that I had to infer from what the problem implied, and also I had freedom in inferring that. I didn't have to reach that conclusion, but I chose to. What would they want to know is the position at 1 second. So what I'm going to say is x of t equals 1.00 seconds is question mark, and this is part A, and x of t equals 2.00 seconds equals question mark. Now, I would prefer to just write that x of 1.00 seconds, but without telling you a priori that this is x as a function of t, that might not be so easy for you to understand. And you might think I'm saying, hey, multiply x by 1 second, or hey, multiply x by 2 seconds. And that's why I took the time to just write x of parentheses t equals 1.00 seconds. So that's just another terminology and nomenclature that I tend to use, or symbols that I tend to use. For part B, it says, what would its speed be at those times? So I'm going to say v of 1.00 seconds, because now I've established what I meant by that terminology. So I'm going to go ahead and write it as just v of 1.00 seconds and v of 2.0, oops, that was not right to write it equals after it. V of 2.00 seconds is equal to question mark. Okay. So that's what I'm using. Now, what I'm going to do is notice that my initial velocity is downward, my acceleration is downward, and my subsequent position should be downward as well. So, unless I just want a bunch of negative floating around, there's really no reason to call down negative. I'm going to choose to call down positive, and you're not going to be wrong by calling down negative. That's perfectly fine. It's just you're going to get a lot of negatives. So in my head, what I'm picturing here is basically an x-axis pointing down, and let's say a hand right there releasing the ball at, in this case, x. This would actually be y in this case, but the main thing is you'd see the ball right here is at x0 equals 0. Okay. So with that in mind, I can now say V0 is going to be positive. I can now say A is also going to be positive, and we can go from there. The big thing is if you're not using a coordinate system, you at least need to figure out, hey, when I use an equation like x equals 1 half at squared plus v0t plus x0, you need to think, is that 1 half at squared contributing to the distance? Or is that actually taking away from the distance? Then you got to do the same thing with the V0t. Is that actually making the distance larger or is that actually making the distance smaller? If you see that one's making it large and the other one's making it small, if you're not using the coordinate system, that should be just a big bell going off in your head saying, hey, these two things have to have opposite signs. And it really doesn't matter which opposite signs you choose. That's just equivalent to choosing X pointing down versus X pointing up, or Y pointing down versus Y pointing up. So keep that in mind. But I generally try to think in terms of coordinate systems because I find it just a lot easier to do that. So now what we're going to do is go ahead and figure out exactly what equation I want to use. What I notice is I have an initial velocity v0. I notice I have an a. I notice I have an x0 that I've actually set up, and I'm asking for an a. So the equation that pops into my head immediately is x equals 1 half at squared plus v0t plus x0. And that's the one I'm going to use. But there are other equations. For instance, we found that velocity average was equal to x minus x0 over, in this case, I just put t instead of t minus t0 or t final minus t is zero. If you look at this, you can see, hey, if I was able to know the average velocity, then I could solve this for x in terms of x0 and t. That would actually work, but I'd have to figure out some other way to calculate the average velocity. Well, that would also say, well, I happen to know that the average velocity when the acceleration is a constant is just v1 plus v2 over 2. So that's that extra equation I could use that I told you guys you could use, even though I didn't derive it. So in principle, I could use these last two equations as well, and that would work just fine. That's part of the thing with physics is almost always a problem that you solve has multiple ways that you can solve it and multiple ways that you get it right. And in fact, if you find multiple ways and they get different answers, it's probably because of a mistake you made. So just keep that in mind. So now I'm going to go ahead with part A and I'm going to use the first equation as I suggested, but I just wanted you to see that, hey, I'm thinking of all the equations that I gave you guys last time and I'm going through them in my head trying to decide which ones have the symbols that I want and the symbols that I have and the symbol, any other symbols that I might not have are not included in it. So x is equal to 1 half times 9.80. I'm going to leave off the units here. I think we've established a little bit about how the units work out, so I don't need to write that. That being said, on a test and even on your homework, I would highly suggest you keep the units in so you can catch yourself making simple algebra mistakes. So 1 half times positive 9.80 times 1.00 seconds squared plus 3.00 times 1.00 seconds plus I've got x0 which is zero point 0.0 meters, and I don't know why I put seconds in there even though I told you I wasn't going to put the units. We'll call that Mr. Younger's a goober. That's the reason for that one. So I know 9.80 times 1 half is 4.90. You guys probably know that from your first experiment where you had to drop that ball 2 meters and solve for half of g. So that's clearly 4.90. and that works out to be 4.90 meters. And then easily enough, this is just 3.00 meters. So clearly the answer here is 7.90 meters, and that's the x at 1.00 seconds. So remember, if you would try to do this without an initial velocity, the answer would have just been 4.90 meters. Notice how the two terms are not intermingled. There's no term that has an a in it and a v0 in it. So in that sense, the two motions are completely separate. You don't have to think that it actually makes it accelerate at a different rate because you're throwing it down versus throwing it up. So that's a big concept to learn, and I want to make sure I pointed that out. Now at 2 seconds, I'm going to get 1/2 times 9.80 times 2.00 squared plus 3.00 times 2.00 plus 0.0. Now, in this case, it's 1/2 times 9.80, which we know is 4.90. Now I'm going to multiply that by 4. 4 times 4 is 16. 4 times zero point 0.9 is 3.6. So instead of getting 16, I'm going to get 19.6. So this term right here is 19.6 meters. And then 3 times 2 is just 6. So the answer in this case becomes 25.6 meters at 2.00 seconds. Any questions on that one? Now I'm doing this arithmetic in my head, and that's just me trying to speed up. So again, don't worry about doing that in your head or anything. Just throw the numbers in. And not only that, please throw the numbers in while we're working it, because I told you when I do this arithmetic in my head, sometimes you'll be like, "Ooh, wow, Mr. Younger's really good at this." And other times you'll be like, "What the heck's Mr. Younger smoking?" So that's what happens when you're doing this. Sometimes it gets really off the track. So it would help me if you find any errors. So that was part A. Now we're going to go to part B. Part B, we're looking for an equation that gives me a final velocity. Notice the x equals 1/2 at squared plus v0t plus x0. Doesn't give you a final velocity. It only has a v0 in it. So that equation is not helpful for this. So the equations that I'm thinking are v squared is equal to v0 squared plus 2ax minus x0. And that actually works. But the problem with that one is I'm going to have to use the x's that I calculated above, the 7.90 and the 25.6. And if I made a mistake in part A, now I'm going to get a wrong answer for part A and for part B. So that's just not good test taking procedure. Yes, it completely works. And yes, it's a good second check. Like if you're wanting to make sure you really got the right answer, by all means use that to confirm it. But what I think would be a better use of my resources is using V is equal to V0 plus AT, which you'll remember was the first derivation that I did in kinematics when I solved the first differential equation last time. This also happens to be the same equation as the average acceleration definition. It's just a matter of, in this case, it's not an average acceleration, it is the constant acceleration. So that's what I'm going to use. V equals V0 plus AT. So V is equal to 3.00 meters per second. I'm leaving off the units again. The A is 9.80 meters per second, and the T is 1.00 seconds. So 1 times 9.8 is clearly 9.8. When I add 3 to that, that gives me 12.8. So the answer is 12.8 meters per second, or excuse me, yes, meters per second at T equals 1.00 seconds. The other one at 2 seconds would be 3.00 plus 9.80 times 2.00. Again, I put seconds in there the last time. I don't know why. Just habit, I guess. But I'll take it off now. So I'm again not putting the units, but I do recommend you do it. 2 times 9.8 gives me 19.6. And of course, 19.6 plus 3 is 22.6. So my answer is 22.6 meters per second at t equals 2.00 seconds. Now, again, you could go back and plug those in with the v squared equals v0 squared plus 2ax and solve for v final. Notice you're going to have to take a square root, and whenever you solve equation with squares in it, you take the square root. That means you can't just take the square root. You have to consider the positive square root and the negative square root. That's why I told you some instructors don't even allow you to use the v squared equals v0 squared plus 2a parentheses x minus x0 because it's not a vector equation, and you've got to be smart enough to recognize whether the velocity will be going down or up, which doesn't seem like a big deal in this problem, but in the next one it will. Anybody have any questions on that? I know I'm sort of steamrolling you by talking so fast, so by all means stop me if you have any questions. Like I said, don't be embarrassed. It's probably, if you have the question, there's probably two or three others that have it too. All right, we're going to move on to the next one then. So you'll notice I'm using 216. The last example I did was like 212 or 214 or something like that. I'm not covering all of them. I'm trying to pick the harder ones. Okay. That does not mean the other ones aren't useful, especially the other conceptual ones. All of the conceptual ones are useful, and you should be making sure you understand all of the examples. Really, what it should come down to is when you get ready to start your homework, that shouldn't be done until you've fully understood all of the examples we've done and you've been through my class where I covered certain examples. Then you should start trying the homework. And if you run into difficulties, then you might want to go back and reread the examples, make sure you understood them, and look for examples closest to the problem you're doing, and then go back and reattack it. If that becomes a problem, then go look for the chapter quizzes that I have for the given chapter you're on, and you can just start doing some of those for practice. Once you're at that point, then you should be obviously ready to go ahead and finish your homework or start practicing for the test. Let's go to this next one. Conceptual example 221. I sort of reworded this too. So, a ball is thrown upward at 15 meters per second. At what time will it reach a height of 8.00 meters above the height from which it was released? So, what we're going to write here is V0 is equal to 15.0 meters per second. And I'm just going to write up with a dot next to it. We also know that acceleration would be 9.80 meters per second every second, and this one's going to be down. So again, I have a case where I just put up and down so I can use that to either set up my coordinate system or choose signs. I also know that we want a final, let's say since it says reach a height of 8 meters, relative to your hand, what we're going to call the position at which your hand releases the ball, we're going to call that x0. And that x0 is going to be 0.0 meters. And what we want is x final to be 8.00 meters. And specifically, it's asking us uh, at what time will it reach a height of 8 meters. So I'll say at t equals question mark. So that's the big part of sifting out what variables I've been given and what variable I need to solve for. Now the part comes up, now that I've labeled them, is going through the kinematic equations and see which one I want to do. As you,
Shouldn't x0 be 0.00 meters so we keep the same amount of sig figs?
yes, that would be much smarter. I usually just ignore sig figs when I'm adding zeros or stuff like that, or multiplying
Okay.
zeros. But you're absolutely right. It should be 0.00. Good job. All right, solution. So your kinematic equations give us this one, x equals 1 half a t squared plus v zero t plus x zero, and that's the one I'm going to use. Since we're throwing the ball up, I think it's best that we treat the upward x direction, and next chapter is going to become the upward direction will be probably y, but right now we're going to say up is positive x and down is negative x. So hopefully y'all now recognize, try to guess the answer here. What do you think my signs of V0 and A would be? I'm going to go ahead and write them down. Again, I'm saying up is the positive x direction, down is the negative x direction, and I'm asking you what sign do you think I'm going to put on V0 and A? Here's the answer.
V0 would be positive and then A would be negative.
Exactly. That's exactly what you want to do. And you're not, you don't have to do it that way. You could still say down is positive and up is negative, but that would give me more negative. So that's why I choose not to do it. But good job, Jaden. So now we're going to go ahead and solve that. Notice what happens. I'm going to plug all these numbers in. The x is going to be 8. Oops, I should probably go back to my blue. I'm going back to my blue. 8.00. I'm going to leave the units off. I highly recommend you guys work this out with the units so you can see the beauty of how these units cancel out and stuff. But right now I'm just trying to conserve time. So it's 1 half. And as you said, negative 9.80 is the acceleration. And then t is what we're looking for here. So that's t squared. And then plus v0, which is positive. So I'm going to write 15.0 plus x0, which is 0.00. For our student that pointed out the 0.00 is better. Now, what I'm going to do is multiply a little bit. This is going to give me 8.00 is equal to negative 4.90 t squared. Oops, I left off a t in this one. Everybody catch that t I just had to draw here because I completely forgot to write it. 15.0 t, and that's the whole answer. What I'm going to do, and I did this the opposite way in class today when I covered it, I'm going to put all the parts of the equation on the left-hand side, so I'll only have one negative instead of two negatives. So when I do that, that's going to become 4.90 t squared minus 15.0 t. And then that would be, of course, plus 8.00, and all that's equal to 0. I think you guys know enough that whenever you have a t squared and a t term, you don't have any choice but to set it up like a quadratic equation where you have a x squared plus bx plus c equals 0. And that implies that x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all that divided by 2a. So if this is a thing that's bothering you in terms of your ability to memorize it or know it off the top of your head, I highly recommend you complete the square on the equation that I drew to the left, the ax squared plus bx plus c, meaning leave it as an a, leave it as a b, and leave it as a c, and this work out the completing the square for it. And by the time you finish that, do all that algebra, you will have this memorized, or at least I did. Okay. Now we're going to go ahead and solve that using the quadratic formula, only we're not solving for x, we're solving for t. So t is going to be, and my pencil keeps stopping writing, it's acting kind of weird. I don't know what's doing that. But t is equal to, now remember, in the term to the left, the ax squared plus bx plus c, notice the uh, signs are all addition. So that means anytime you get a subtraction, that means you're supposed to say that coefficient is negative. So just keep that in mind. In this case, the negative b would be positive 15. Oops, I should probably write in pen instead of laser pointer. So that's going to be 15.0 plus or minus the square root of 15.0 squared minus 4 times a. A is 4.90. times C, and C is 8.00. And then all of that's going to be divided by 2 times A, which is 2 times 4.90. Again, if you did this in units, you'd be kind of impressed at how all the units work out. Now, I'm going to get 15.0 plus or minus the square root. 15 squared is 225, and that's the proper number of sig figs, so I'm going to leave it like that. Now I'm going to get minus, and in this case, if I multiply 2 times 4.9, I'll get 9.8. If I multiply 4 times 4.9, then I'm going to get 19.6. And then I got to multiply 8 times 19.6. That's getting in that realm where I'm really likely to make a mistake. So I'm going to go ahead and say 8 times 19.6 on my calculator. And that gives me 156.8. Actually, let me check everything. 4 times 4.9 times 8. Yes, gives me 156.8. So notice there's a little sphincter check here, if you will. Sorry about the terminology. I can't believe I just used that by accident. Uh, but anyways, we've got a issue under the square root where we could have gotten a negative. So that was a little bit harrowing experience, if you will. Because if you get an imaginary answer in a physics class, other than quantum mechanics and a couple other weird little things, then you know you've done something horribly wrong. So in this case, it works out. By the way, the 4 times 4.9 times 8.00 is only 3 sig figs. So the 8 is not a sig fig. I'm going to take 225 minus 156.8, and that's going to give me 68.2. So I'm going to get 15.0 plus or minus the square root of 68.2. Notice in subtracting these, we get 225 minus 156. That only leaves me 2 sig figs uh, to the left of the decimal, and we only had one of the numbers had one decimal place, so the 2 is not a significant figure. And the 2 times 4.8, of course, is 9.80. So now what I'm going to say is therefore, T is equal to, and I'm just going to take the top sign, which is 15 plus, work that out, and then I'm going to take the bottom sign, which is 15 minus, and work that out, and that'll give me two answers, and then we'll have to analyze it. So the square root of 68.2, I'm going to say that's raising it to the 0.5 power. That turns out to be 8.258. So this is 15.0 plus 8.258. Now, taking the square root of 68.2 with only two sig figs means I only have the 8 and the point 2 as significant figures, and then that's going to be divided by 9.8. So I'm going to take this 8.2583 blah blah blah, and I'm going to add to it 15. That gives me 23.258. Now I'm going to divide that by 9.8, and that gives me 2.373. And that works out to be seconds, which you can't see because I didn't actually use the units this time, but it is correct. Notice the 15.0 and the 8.2 both were good in addition to one decimal place. So that means the first three on the answer is actually correct. But that's all we can get is basically, well, actually 15.8, 15 plus 8 gave me 23. So I take that back. We actually can get one more. So 2.37 is the actual answer. And that's because 15.0 plus 82.2 gives me 23.2. That's 3 sig figs divided by 9.80, which is 3 sig figs. So that's why I can get 3 sig figs. Now the other answer, remember it's actually read plus or minus, so I'm going to say or T is equal to, in this case it's 15.0 minus 8.258. And that gives me 6.742. And notice in this case, again, it's only good to one decimal place. So in this case, I only get 2 sig figs, but now I'm dividing it by 9.80, and that gives me 0.6880 actually. And that's seconds. In this case, we only had 2 sig figs, so the 8 and the 0 are not sig figs. So I ask you this, we just got a time of 2.37 seconds and another time of 0.69 seconds. Uh, is one of these right? Is both of these right? If one of these is right, which one's right? Or none of them right? Did we just make a careless mistake? How will we possibly get two? Does anybody have any idea?
Because it has to come down.
Exactly. So yeah, there's an 8 meters it hits on the way up. Obviously, that should be the 0.69 seconds. And then there's another one that it hits on the way back down, and that should obviously be the 2.37. Okay. So yes, absolutely. You will also see this later when we start doing projectile motion. We'll have like an object shooting off a cliff. Let me show you a drawing of this. So I'm going to go ahead and circle these off because they're really both good answers. One of them's on the way up, the shorter one, and the other one's on the way down. That's the longer one. But if you, for instance, imagine firing a projectile off of a big plateau like this, you can say it has some initial velocity v0 at some angle theta, and it's going to go and fire like this. And then I'll ask you a question like, uh, at what time will the projectile hit the ground? Ooh, I don't know what happened with that word, the. Whoa, I don't know what happened there either. So if I asked you that, then what you'd do is end up solving another quadratic equation, but you'd get two answers. And one answer would be t equals some number like negative 0.97 seconds. And another answer of 2.4 seconds or something like that. In that case, what you're actually seeing is there exists an equation for the parabolic motion that you get in projectile motion, and that handles a whole parabola, which in this case might look at least like this part. So when you get that negative 0.97 seconds, that's how long in the past a projectile had to be fired from ground height so that at 0.97 seconds later, it would reach the height of the plateau with exactly the velocity v0 at an angle theta that it had. So these multiple times tend to mean real stuff. It's just a matter of figuring out exactly what it means. You'll get more of that when we get into the next chapter. Anybody have any questions on that? All right, we're going to move on. These are a little more difficult. I just noticed that traditionally students sometimes forget that you're sort of expected to know quadratic formulas and various other things you learn. Synthetic division, for instance, sometimes comes into play. Regular division of polynomials comes into play in physics. They just sort of forget that, everything that they've ever learned in all their past math classes up through Calc 1 is fair game. So I wanted to make sure I refresh you on the quadratic formula. There are harder problems than this. For instance, you can do weird questions like a projectile is thrown up at ground level with such and such a velocity at how long will it take to pass a window that's the bottom of which is 3 meters above the ground and the top of which is 3.7 meters above the ground? Doing stuff like that is a very real type physics problem, and in many ways it's way more difficult than this. So just be prepared. That's the kind of stuff I don't want to work all those. I want you to use your creative mind to figure out ways to solve that. You'll see that's one of that is very much like a couple of the problems that are in the practice bank as well as the main bank that we use for the bank for the tests. All right, let's move on to the next example, and this is the scary one I warned you guys about. So this is the one where, if you're a little bit antsy about your calculus, don't worry about it. I'm showing you exactly how to do it, okay? Not only that, it looks exactly the same way as what we did last time where I used it to derive the kinematic equations. So here it is, a made-up problem. The acceleration of an object is given by a of t. Remember that function notation that we use. A object has an acceleration given by a of t equals 3.00 t squared. And actually, I meant to actually put that 2 as an exponent, but I left the caret symbol on there, so that's okay. And has a position of x equals 1.00 meters at t equals 0.0 seconds, and a velocity of 2.0 meters per second at t equals 0.0 seconds. Derive expressions for the velocity and position as functions of time. So this is just like the problem we did last time in deriving the kinematic equations, only we said the initial position was x0 and the initial velocity was v0. This is the same thing, except I'm actually using a number. The other thing that it's not is the a is not a constant anymore. And one of the questions that often accompany a problem like this is I might ask you, what would the units of 3.00 have to be for this a of t function? I want you guys to think about that and feel free to blurt it out when you think you got the right answer. So, what would the units of the 3.00 need to be, knowing that acceleration has to come out in meters per second every second, which is written meters per second squared, and knowing that time has to be put in seconds and it's going to be squared. So go ahead and think about that. See if you can figure out what that unit is. That's a very typical problem that should be asked. Now I'm going to go ahead with the solution, and I know the answer off the top of my head, so I'll certainly correct you if you get it, or if you get it wrong, or I'll pat you on the back if you get it right. So our solution
Can you
here.
rephrase how you asked that?
Mhm.
You're saying the answer, we're trying to figure out the unit of the answer, the
No,
final answer?
we're trying to figure out the unit of the coefficient, the 3.00, which is a coefficient of t squared, knowing that t is going to be entered in seconds, and knowing that a of t has to come out in meters per second to the second power. So that's what we're
Oh,
trying to do.
so it's meters per second?
No, not quite. Remember, the t is going to be squared, so that's a second squared. And we need, even though we're multiplying by second squared, we need that unit to come out to be meters per second squared.
So is that meters per second to the negative fourth?
Exactly. Except for when you say
Sorry,
per
meters
and
seconds to
minus.
the negative fourth.
Yeah.
Right.
Yeah. You double said it when you did that. But yeah, absolutely right. It's meters per second to the fourth power is what the unit on the 3.00 would have to be. So make a note of that so you guys can figure that out if you didn't already. That's just a good skill to learn, and it's something that'll help you in your engineering classes and your physics classes and your chemistry classes. All right. So what I need here is we need some fundamental answers. Like we know acceleration is dv dt. We also know that that velocity is dx dt. So that's some of the stuff we need to know. What we do know is x of t equals 0.0 seconds. Here's that same sig fig issue we were having before, but again, notice it's 0, so I didn't care too much. That's going to be 1.00 meters, and this is what we call an initial condition. And you can tell why it's initial. It's the condition of x when time is 0. But to be honest with you, you don't have to actually have initial condition. You could have a value of x at any time t and just put that in there, and that would be acceptable as well. It's just a lot easier if it happens to be an initial condition, because when the initial condition is used, then the t is going to be 0, and you'll see that makes the arithmetic a lot easier. The other thing we have is V of t equals 0.0 seconds is going to be 2.00 meters per second. So that's what we're using here. So I'm going to start off by writing 3.00 t squared, and I'm going to leave a space, and you'll see why that space is here in a second. And then I'm going to say dv dt, and I left another space there. So this is a first order differential equation as it's written right now. If I chose to put in, instead of dv dt, if I chose to write d2x over dt squared, it would be what we call a second order differential equation, because obviously it's a second order derivative. But the way we solve it isn't too difficult. This is a separable differential equation. It's supposed to be really easy. And what we're going to do is, and I'll show this in a different color just so you can see that it's multiple steps here. The first thing I'm going to do is multiply both sides by dt, because you can do anything to an equation that you want as long as you do it to both sides. So that's what I'm doing here, and I'm going to put this in parentheses just to make it a little more clear, like this. Okay, so now I've multiplied both sides by dt, and I can see that the right-hand side's just going to sort of cancel out like the chain rule taught us. And now I'm going to integrate both sides, and I'll do that with red. Okay, so I'm going to go ahead and do it like I did last time, where I'm going to use the leave the limits of integration off. But I would like to tell you what the limits of integration would be if you chose to do it that way. So I will write this in green, but we're not going to use it. I just wanted you to know what it would be. Since we're integrating the left-hand side over t, this would be understood to be an integral from t equals 0 to a time t, and that pretty much makes calculus and math teachers roll over in their grave. So that's not something we'd normally do. They would normally call the t tau or something like that, and just recognize they'd put the t in the integral and the t in the t squared. They would replace that with tau and then integrate from tau equals 0 to tau equals t. But we don't care about that in physics. We just roll with it. Okay. The right-hand side, since we're ultimately going to cancel out the dt's, we're just integrating dv, then that's obviously from v0 to v of t. And that's what it would be if we chose to use the limits of integration, but again, I'm choosing not to do that. So now we can integrate 3.00 t squared. And I think you all realize that should be 1/3 of 3t cubed. So I'm going to write that down. 3.00 divided by 3 times t cubed. Now, since I didn't use the limits of integration, I have to put a constant of integration on here. So I'm going to say plus c. Now, technically, you do it for both sides, but you have a c on the left, you have a c on the right, you subtract the c on the right from both sides, and then you have a c plus c on the left. That's just a new c, so why not just call it a c in the beginning? That's what's going on here. So I don't have to put another c over there, but I think y'all probably get that. Now the right-hand side is just going to be v. Now that's technically v of t, but now we need to use the initial conditions to actually figure out what that c is. So I'm going to say right here, initial conditions IC implies, notice the 3.00 divided by 3 is just going to become 1.00. And then t cubed, since we're doing at t equals 0, that's 0.0 seconds cubed plus c is equal to, now remember the actual velocity at t equals 0 seconds is 2.00 meters per second. And you see now the advantage of it being an initial condition, because t equals 0 made that whole term disappear. So I automatically found, therefore, c is equal to 2.00 meters per second. And we'd say v of t is equal to, now we can say it's just 1.00 t cubed plus 2.00. And we know that unit's supposed to be meters per second. We don't really need it that much, though. Okay, so that's what V of t is. Anybody have any questions on that step? All right. So that's V of t. Now I'm going to go back and use my definition of velocity being the derivative of position with respect to time. So I'm going to, again, leave a little space because I know what's coming. And I'm going to write this is equal to dx dt. Notice I'm scrapping that V of t part. I don't need that part. Okay. But I've now got another differential equation. And the way we're going to solve this differential equation is the same way we did before. We're going to multiply both sides by dt. I'm going to do it in a different color again so you can see the different steps. So multiplying both sides by dt, I get that. Now I'm going to take the time to integrate. And again, I'm going to do that. By the way, we could do the limits of integration here. And if I did so, what they would be was on the left-hand side, I'm going to say from t equals 0 to t. And on the right-hand side, I'm going to say from x0 to x of t. Okay. If you did that, it actually is it's a lot easier. There's no step like I had to do before where I had to solve for c. That's kind of the beauty of it. But again, you don't need to do that. I just wanted to make sure you knew how if you wanted to. So now that I integrate this, I'm going to get the following result. The integral of 1 t cubed is going to be 0.250 t to the fourth, because it has to be 1/4 t to the fourth, and 1/4 of 1 is 0.25. And of course, 1 had 3 sig figs, so I wrote it as 0.250. Now, the integral of 2 becomes 2t, so I'm going to say plus 2.00 t. Now, we still have a constant of integration, so I'm going to say plus c, and that's going to be equal to x. So now I've got an equation. Now, technically, that's the equation for x of t, but I have a c in it that I haven't figured out yet. So now I've got to use the initial conditions again. So the initial conditions tell me that at t equals 0, x of t is equal to 1.00 meters. So I'm going to say 0.250 times 0 to the fourth power plus 2.00 times 0.0 again plus c is equal to 1.00 meters. Therefore, remember these 3 dots in a triangle means therefore. Therefore, c is equal to 1.00 meters. Now I've got a final result here, and the result is x of t is equal to 0.250 t to the fourth plus 2.00 t plus 1.00. If I wanted to write this in numbers, I mean with the units, I would say x of t is equal to 0.250 meters per second to the fourth power times t to the fourth plus 2.00 meters per second times t plus 1.00 meters. And that's the final result for the x of t. And this is the final result. Ooh, I called that x before and I meant to write it as v. Oh, let me go ahead and write what that was. V of t was equal to 1.00 meters per second to the fourth power times t cubed plus 2.00 meters per second plus 3.00. Oh no, that was it. Any questions on that?
Yes. I see how you got to the from one and t to the third to 0.25 t to the fourth.
Hmm.
I'm not sure why the two doesn't change at all when it goes from just two to two and no, wait, I see it
You
now
see
because
it
you're
now?
adding the
There you go. Good
yeah,
job.
never mind. I just had to say it out loud. Never mind.
Yeah. Yeah, sometimes that's all it takes. So yeah, good job. And it's not about whether you would have thought of this on your own to do it. It's about, hey, Mr. Younger showed me this. Now I just repeat that and I can do it myself. So don't feel bad if you weren't able to come up with this on your own. That's the whole point of teaching, and that's where I come in and help you. Okay. So I will tell you the practice test and therefore the online test and therefore the face-to-face test has problems very much like this in the bank, but they actually take it a step further. They'll not necessarily ask you explicitly for x of t or v of t. They'll just say, uh, they'll give you the same initial conditions, what the acceleration is as a function of time. They might give you the position at t equals zero. They might not even give you that because it turns out a lot of times you can just cancel that out. But they'll follow it up and say, what's the average velocity from t equals 1 second to t equals 4 seconds? So it's the exact same process that we went through here, only I don't give you or in the problem set doesn't give you the actual x zero, but you know it's going to be x zero, so you can just call it x zero. And then later, when you do x at 4 seconds minus x at 1 second, that x zero just cancels out, so it didn't matter that you didn't know it. So that's like the next level, and that's really the types of questions that they ask you in the bank, and therefore in the homeworks as well. That's a possibility. Specifically, though, when I say that, I don't think they put one in the homework set that I assigned you, but they have it in the problems at the end of chapter 2. So that's a more robust collection of homework problems for chapter 2 is the problems at the end of the chapter. And remember, the odds are actually have the answers in the back so you can work them out. Anybody have any questions on this? There's plenty of them on my YouTube channel as well. Remember, I actually have a list of my YouTube channel videos with their titles, and the titles are pretty descriptive. But the video list of videos is in my helpful documents and links, and it's called My Video List underscore by Austin, and it has a date on it, like 9/3 or something like that. All you have to do is click in there, and you can just do a search for kinematics or acceleration, that sort of thing, and it'll show you all the videos in there. And then not only that, it has a link to them, and the title tells you how long they are, all that good stuff. Anybody have any questions on that? All right. Well, now we've got to jump into chapter 3, and chapter 3 is on vectors or is on motion in 2 and 3 dimensions, and some it says colon vectors because we are going to cover vectors in there, but we're specifically going to also up this kinematic stuff from just 1 dimension like we've been doing in chapter 2 to 2 dimensions and possibly 3 dimensions. So it'll actually include projectile motion where you fire an object not only down or up, but up and to the left or down and to the right, that kind of stuff. Any questions on that? All right. So in order for you to do that, we need to know vectors and we need to understand how to work with vectors. Is there anyone in here that didn't cover vectors in your pre-calculus trig class? I'm just curious how many people end up getting a pre-calculus class, the trig part that doesn't have vectors in it. In my class of 24 this afternoon, or 20 something this afternoon, I had two people that hadn't, and that is okay. It's not that big a deal. I will show you from the very beginning exactly what it takes. But I just wanted you to, be advised that it is covered there, and often you'll find it. Uh, Even if you found it really hard, then the second covering might not be because of me. It's not that I necessarily did anything great. It might just be the second time covering it made it more clear. So what I'm going to tell you is we're going to go over vectors. As I mentioned in class, Despicable Me has a really good definition of a vector. Specifically, the movie Despicable Me had the bad guy was named Vector. And he said, it's a mathematical term, and it means a quantity that has magnitude and direction. And he said he chose that term because he does evil with direction and magnitude, right? So that is an actual good definition of vectors, and I always look for anything in everyday life that allows us an opportunity to think about calculus or physics or any of that kind of stuff. So hopefully that's something that will keep it in your mind a little straight, a little bit longer. We also want to remember that the quantity vector or the word vector starts with a V, and the quantity that we saw earlier was a velocity, which also starts with a V, and velocity is a vector quantity. So hopefully that's a little mnemonic that'll help you remember what a vector is, which one's vector versus which one's not a vector. The other thing is speed was a quantity we discussed, and speed starts with an S, just like the scalar starts with an S, and a scalar is what speed is. Now, there are other vectors. For instance, force is a vector. Acceleration is technically a vector, but a lot of times people just use the word acceleration and they mean the magnitude, in which case it wouldn't be a vector. But generally speaking, in the physics world, acceleration is a vector, force is a vector, uh, torque is in some sense a vector. Stuff like that. Momentum is another quantity that's a vector, but there's quantities that are scalars too, like mass or temperature or time. Those are scalar quantities. So I also want to tell you that the quintessential example of of a actual vector quantity is what we term the displacement vector. So let me show you what I mean by that. Let's imagine that this is your house and there's your front porch. Okay. And let's imagine that you're going to walk from your front porch right there. That's you, that little dot. Okay. And I'm going to further say that this is in a neighborhood and that your house runs from west to east, left to right, and it runs from north to south, back to front. Or excuse me, from south to north, back to front. So if you imagine a two-leg trip, in other words, a trip that you take from your front porch that involves one leg walking one direction and then another leg of the trip is walking an entirely different direction, that gives you two displacement vectors. So I'm going to say, first off, you're going to walk a distance of, and actually, let me make this a little better so it's a little easier. I'm going to make your porch a little better so that I can just walk off from an actual uh, vertex on my graphing paper here. So now that's your front porch, and now this is you right here. Okay. So the first leg of your trip is going to be a walk that is going to be, let's say each of these squares is 3.0 meters and 3.0 meters. That's the scale we could use. One square is 3.0 meters. So this part right here would be displacement 1. And the way we indicate a vector is we normally use a capital letter. There are sometimes where you use small, lowercase, but we normally use a capital letter. And then we put an arrow over it if we're doing handwriting. A lot of textbooks just make it bold print when it's a vector, but your author, Giancoli, uses the bold face and the arrow over top. And there's a lot of different ways you can draw the arrows, so don't feel bad about that either. So the first leg of our trip was a 1, 2, 3, 4 square, therefore 12 meters. And we would indicate that by saying the magnitude of D1, which can be written with absolute value bars. Another way of writing it, this is what they normally do in math departments. They'd write it as D1 with double absolute value bars. And another way that we do it in physics is we just write it as D1 is equal to 3 times 4 is 12.0 meters north. Okay, so we would say the vector D1 is 12.0 meters due north. That's the way you could specify a vector. You could also say it's, which is not in this case, but you could say it's 15 degrees east of north. That's another way of specifying it. Or you could say it's 80 degrees north of east. That would be another one. All that's different terminology that we'll use, and you can see that in the video on the world's greatest vector addition problem. Now we're going to consider a second leg of the trip. And the second leg of the trip is going to go 1, 2, 3, 4, 5 squares to the right. And this is the vector D2. So the magnitude of D2 is going to be 5 times 3. 1, 2, 3, 4, 5. That's 5 times 3. And 5 times 3 is 15.0 meters. And we would also say that D2 is equal to 15.0 meters due east. Okay? So that's another way we express it as well. Now, when I say the displacement vector is an archetypal vector, what I mean by that is this is a case where you can just obviously, knowing what displacement means, you can obviously figure out what the vector sum of D1 and D2 is, because we know the vector sum is basically the definition of the displacement. And remember, the displacement vector is a vector that points from where you were to where you ended up. That's your displacement vector. So I'm going to draw that in red, and I'm going to say it goes from where you were to where you are now. This is D1 plus D2 vector addition, and I'm going to call that R, because another word that we use for the sum of two vectors is the resultant. So D1 plus D2 is the resultant vector, therefore I called it R. Okay? So what we saw was if I took a trip due north 12 meters and then hung a right and took another trip 15 meters due east, my total displacement is the sum of those two displacements. So that is vector sums. And these two vectors are said to be in head to tail position. Notice the head of D1, the arrow, is at the tail, which is the part without an arrow, of D2. That's what we mean by head to tail. So now we've learned, at least as far as two vectors go, all we have to do to add two vectors graphically is we draw a arrow from the tail of the first to the head of the last. So H2T, draw a vector from tail of the first to the head of the last. Now, I said last because I only did 2 here, but you should see that it would be obvious if we did a series of trips like this. Let's say I walk this way, and then I walk that way, and then I walk that way that far, and now I walk this way that far, and now I walk this way that far, and now I walk this way that far. Okay, then we know automatically the resultant of that is from here to here. That would be R. So the answer is prescriptive, meaning it actually tells you how to do it in all cases. Not only that, we can learn something very specific because I could have drawn, watch this, if I drew D2 first, in other words, instead of walking due north first, I walk due east first, and then I walk due north. Then this blue vector, because vectors only have magnitude and direction, the vector here, the blue one to the right, has exactly the same magnitude and direction as D2, so it is D2. And the blue vector going up, that has exactly the same direction and magnitude as D1, so it is D1. So now we've learned that A plus B is equal to B plus A. That's one of those rules you learned in pre-algebra, and of course you recovered it in Algebra 1 and Algebra 2 and all that good stuff. But it turns out that those rules are very important. Those rules are hinting at what's to come. There's an idea of an algebra and an idea of a space, and an algebra is a collection of things that obey these rules, and a space is where those collections of things live. So when you take linear algebra, for instance, that's one of the things you'll learn is to define a vector space and then prove that it's a vector space and that sort of thing. You'll find out that the rules required for something to be a vector space are basically those same rules that you learned that made no sense, like A plus parentheses B plus C, close parentheses, is equal to parentheses A plus B, close parentheses, plus C. That's another rule, right? Or A minus B is defined to be A plus the negative of B. You'll see that comes in handy as well. So now we've learned a couple things already from vectors, just from studying displacement. What about something else? There's another way that vectors can be organized, and it's not head to tail. So, for instance, what is the sum of two vectors if they're tail to tail? So let's draw this vector, A, and this vector, B. And these vectors are, I'll write it in non-cursive, tail to tail. So if you have two vectors tail to tail, what do? Well, the answer is right in front of us, because if we look at vectors D1 and D2 that we already did, we can see that this version of D1 is actually tail to tail with this version of D2. And it turns out that D1 plus D2 is a diagonal of this parallelogram, which in this case happens to be a rectangle, but it's a diagonal of this parallelogram. So all we have to do is complete the parallelogram. A way we can think about completing that parallelogram is we can imagine this vector B sliding along this vector A. So I'm going to take that same vector B, which goes down 1 and over 3. I'm going to assume it goes down 1 and over 3, which means it's going to end up right there. So down 1 and over 3 ends up right there. And now I'm going to take vector A, and I'm going to imagine it sliding along vector B. And when I do that, I will get, notice it goes up 3 and over 2. So I'm going to go over 2 and up 3, which means it's going to come right here like that. So this red vector on the right is exactly parallel and the same length as A, and this red vector at the top is exactly the length and parallel to B. So I have completed the parallelogram, and what we saw is the solution to this vector addition problem is drawn from the common tail to the common head. Common tail to common head. So finally, we can say our vector sum is that. So that is A plus B is equal to R2, say. So the answer for tail to tail is complete the parallelogram. Parallelogram and draw from common tail to the common head. So that's how you're going to add vectors when they're tail to tail. If you have more than 2 vectors, it's kind of a mystery what you do, but our rules that I told you about in pre-algebra, which was A plus B plus C is equal to A plus B plus C. In vector world, that just becomes the same formula, but with little vector arrows over it. So what that means is you can add 2 vectors, any 2 that you want first, and then add the third vector to it, and that's the equivalent of adding 3 vectors. If you had 4, you can do the same thing. You can add the first 2, and that'll get you a third. Then you can add that first solution with the third, and that'll get you a fourth. And then you can add that that second solution with the fourth, and that'll give you the total. So I could do this nasty thing that we saw right here. I could do it at 2 vectors at a time. I could first do it with these 2 guys, which would be a solution like that. Of course, they'd have to be tail to tail, so it would be a solution like that. And then I could take this solution and this vector right here and complete the parallelogram. That would put that like there. And then I could keep doing that over and over until I hit all the vectors, and the final result would be correct. So that's how you do it graphically. Now, if you have access to Invent or AutoCAD or something like that, you can use these techniques that I just taught you to work out exact solutions, because AutoCAD will give them to you exactly. They'll tell you exactly what this angle is, what that angle is, what this magnitude is, all that good stuff. So at least now you know how to add them. I have to next cover what happens when you multiply a vector by a scalar. I only got 3 minutes. Let me do that really quickly. If I told you that we were going to take a run from the middle of the middle of the West Coast due east, and we're going to go 1,500 miles due east, that is an idea of a vector. If I then said, hey, I want you to go twice as far, in other words, your displacement is twice as big, how long would that vector be then? So the original problem was you're running from the middle of the West Coast due east 1,500 miles. I think I might have said a different unit a second ago, but 1,500 miles from west to east. And now I want to take a twice as long of a trip. So how long is that vector?
3,000 or 30,000?
Yeah, 3,000 exactly. So that should be a very good explanation of what happens when you multiply a vector by a scalar. The difference is, though, if you multiply a vector by a positive scalar, then you're just going to stretch it or shrink it. If the number's smaller than 1, you're going to make it smaller. If the number's bigger than 1, you're going to make it bigger. But if it's negative, what's going to happen is you're actually going to flip it over. So if I said, hey, I want you to take a trip from the middle of the West Coast, due east 1,500 meters, the opposite of that trip would be the equivalent of multiplying it by -1. And I think you all get the opposite of that trip would be going from the middle of the West Coast 1,500 miles due west. So here's the solution that we need. Let's say this guy right here is A. Then this guy right here is 2A. I need a vector symbol over that. Notice it's twice as long, but it's exactly parallel. Additionally, this vector right here is 1/2 A. Notice it's only half as long. We could also say this vector right here is -A. Notice the only thing that happened is I turned the direction opposite. If I wanted to do -2A, then that would come from here all the way to here, and that would be -2A. So that's what you actually do when you multiply a vector by a scalar. If the scalar is bigger than 1, you're going to stretch it by that factor. If it's smaller than 1, you're going to compress it by that factor. If it's negative, you're still going to do the same thing, but you're also going to flip it backwards. So you're going to put the head on the opposite end. Does everybody get that? Because we're going to use that next to learn that A minus B is A plus, and this is actually the definition of subtraction, by the way. It's A plus the negative of B, which again seemed like a stupid rule when you learned it in pre-algebra, even though it helps you once you finally got the negative, adding negative numbers, but that should do it. So we'll start here next time. By all means, start watching some of the videos where I introduce vectors. You can get a little bit ahead and this won't lose you, but you're free to go. So thanks for coming, everyone. I'll wait for the last person to leave in case anybody has any questions, but I do appreciate you coming. Don't forget to get your test done, everybody.
Thank
Test
you.
due Sunday. You're welcome.
Thank you.
Thanks, Colin. You too, Zach. Thanks, Jaden. Ian, did you have a question, sir?
Sorry, I was typing it out, but I guess I.
It's no problem.
Sorry, sorry if you can hear my dogs in the background. But
That's all good.
do
Hear
we
my dogs
take
this semester
the
too.
yeah? Do we take the derivative or do we take the integral to get from acceleration to velocity?
Yeah. So you can sort of picture it like this. X is down here, and you take the derivative to get to V, and then you take the derivative of V to get to A,
Okay,
and
so
then you
integrate.
take the integral to go from A to V. Yeah, exactly.
Okay,